Okay, welcome to GADEP's Geometry, Arithmetic, and Differential Equation of Period. Today we have Henrik Bachmann, who is going to talk about finite multiple zeta values. Okay, Henrik.
Yes, thank you very much for the introduction and also for the invitation to speak at this seminar here. So this seminar is about periods, and in my talk there are two types of periods appearing. So the first one will be multiple zeta values and the periods of modular forms given by their period polynomials. And the main object of this talk, as the title suggests, are so-called finite multiple zeta values, which are somehow inspired by these classical multiple zeta values. And in this talk, I will give an introduction to multiple zeta values, then talk to their connection to period polynomials of modular forms. And then we'll talk about finite multiple zeta values, and we'll also mention a conjecture which relates these two objects. And then I will mention a joint work with Yoshihiro Takeyama and Koji Tasaka on the so-called Kanekus Zaghi conjecture, which relates these finite multiple zeta values with so-called symmetric multiple zeta values. And we somehow give evidence for this conjecture by introducing some object lying above this with two maps going in these two directions. And I was told that this seminar is for a broader audience, so I expect that not everyone is familiar with multiple zeta values, and especially with these finite multiple zeta values, but especially here in Japan, there are a lot of people working on these finite multiple zeta values, so I thought it's a good idea to advertise this object to the other side of the planet. So actually I looked up that Nagoya, if I would dig a hole through the earth, then I would come out in the south of Rio in the ocean. So it's almost on the opposite side of the planet. So I think it's a good thing to also bring this topic to the other side. Okay, so let's start with the classical multiple zeta values, which probably already appeared in this seminar at some other talks. So these are given by these infinite sums, where I have some integers k1 up to kr, where k1 needs to be greater or equal to 2. So this sum converges absolutely. And they generalize the classical Riemann zeta value. So if this r is equal 1, then this is just the Riemann zeta function. And so these are real numbers. And by z, we denote the space spanned by these, the q vector space spanned by these real numbers. And then by zk, we denote the space spanned by multiple zeta values of weight k, where the weight is the sum of these indices, and the depth is this r. So they are defined by these sums, but multiple zeta values can also be written in terms of iterated integrals. And I just give one example here. For example, zeta 2, 3 can be written as this iterated integral here. So you see for each index, for example, this 3, I will have a block of this form here, where I have two types of differential forms. For each index, I have a block like this. And this you can easily see by expanding this here with a geometric series and then taking the integral. And if you do this, then you will end up exactly with this sum. Okay, so then when you multiply two of these real numbers, then there are actually two ways to do this. One simple way is so I just give one example. So this is called the harmonic product. This comes from the definition as these iterated sums. So for example, if I take the product of two multiple zeta values in depth 1, meaning just the Riemann zeta value, then I have the product like this. And now I can split up this summation here into these three parts, where either this m is greater than n, or the other way around, or where they are the same. And then I see that this here is exactly this zeta value, this multiple zeta value in depth 2. This here is exactly this. And if they are the same, then the exponents add up, and I have, again, here the single zeta value. So this is one way to multiply two Riemann zeta values. And another way is by taking this iterated integral expression. Then you have these two types of differential forms. And if you take a product of these two iterated integrals, what you basically do is you shuffle all these integrals into each other. And then you can see that if you take a product of these two Riemann zeta values, you can also again express it in terms of double zeta values, meaning multiple zeta values in depth 2. Yeah, so there are two ways of multiplying these, and therefore since this product is the same here, I get a linear relation among these real numbers. Yeah, so in this, these types of relations are called double shuffle relations. And here one explicit example, if I take the slide from before and choose the numbers 2 and 3, then the harmonic product is this, and the shuffle product is this. And therefore, we get this linear relation here. Yeah, and this gives a big family of Q linear relations among these real numbers. But already Euler noticed that there are a little bit more. So for example, Euler showed that zeta 2 equals zeta 3, which cannot come from this type of multiplication, because then I would need to multiply zeta 1 with zeta 2, and zeta 1 doesn't converge. But there's a way to somehow regularize these types of relations, which then gives the so-called regularized double shuffle relations, or sometimes also called extended double shuffle relations. And this one can write down explicitly in all defs. And then one main conjecture in this field is that these types of relations actually give all Q linear relations among these real numbers. And in particular, because all the relations which come from these extended double shuffle relations are in the same weight, we expect that the space of multiple zeta value is a direct sum. So it's graded by weight. So there are no relations in different weights. And then due to computer experience, Zagi conjectured that the dimension for the weight k case can be given explicitly. And so there are two ways to write this down. So one way is using generating series. So if you take the generating series of the dimension of zk, then the conjecture is this is given by this rational function here. But also, if you would call this here dk, then you could see that if you have the generating series which is given by a rational function, then this gives some recursive formula for the coefficients. So you could give some starting values and then say the dimension satisfies this recursion here. And then somehow a finer version of this conjecture is given by Hoffman, who conjectured that this set here, so the set of multiple zeta values where as entries I just take numbers 2 and 3, that they form a basis. So and if you count these, then you will see that you end up actually with the same numbers, and therefore, of course, this conjecture would imply this conjecture here. Okay, but this conjecture is not proven. The only thing we know is that these numbers, which are given as the coefficients of this rational function here, that they give upper bounds for our dimension. So this is independently proven by Terasoma and Delin-Goncharov, who showed that the dimension of zk for any k is bounded above by these numbers dk, which come from this as coefficients from this rational function. And somehow the best result for this Hoffman conjecture we have is due to Francis Brown, who showed that these elements where the entries are 2 and 3s, they at least span the space. But of course, we don't know if these are linearly independent or not. Yeah, so in particular, every multiple zeta value can be written as in terms of multiple zeta values where we just use 2 and 3s. Yeah, so
Henrik, the irrationality of zeta 3 follows from the conjecture or from one of the theorems? I'm just wondering.
Yes. So if this conjecture here is true, for example, if we know that we don't have relations in different weights, then this would mean that all odd zeta values, for example, are transcendental. Because if they wouldn't be, then they are 0 of some polynomial. But this would mean that I have different monomials where I plug in the zeta, and this would give a linear combination of multiple zeta values of different weight. So if we know this, then in particular, all odd zeta values would be transcendental. Yeah, and this we even don't know for any odd single zeta value. So this is a really strong conjecture where we actually don't know much. Yes.
May I ask one question?
Yes.
So you give 2 index, right? One is the depth, another is weight. Is there some conjecture consider these 2 grading together?
Yes, this is a wonderful question because the answer is yes. There's this so-called Broadhurst-Kramer conjecture where you also include here a second variable y for the depth. So let's say ZKR is the space of depths R and weight K. Then there's an explicit conjecture by Broadhurst and Kramer. And this is a good question because this also includes modular forms and somehow has to do with the stuff which I will tell later, the connection of period polynomials and modular forms. But yes, so there's an explicit also, yeah, it's a little bit more complicated, but in this explicit conjecture, you can also find the generating series of the dimension of cusp forms.
Okay.
Yes, thank you for this question. Okay, so we have this, so we can write every multiple zeta values in terms of 2s and 3s. Okay, so this is somehow the classical crash course on multiple zeta values, and now the connection to modular forms. So this was done by Gangel, Kaneko and Zagi, or it's also hidden in this Broadhurst-Kramer conjecture I mentioned. And the rough version of the theorem I want to present is the following. Namely, they proved that modular forms of weight k give relations between these double zeta values, zeta rs and zeta k, where these r and s are odd. And I will make this precise in a second, but here's one example. For example, in each weight k, we have the Eisenstein series, and the Eisenstein series always give this relation here, which is just the sum of all double zeta values where the entries are odd. And then the statement is this is always 1/4 times zeta k. And then the first interesting, or the first non-trivial cusp forms we have in weight 12. So by modular form here, I always mean modular forms for the full modular group. So here the Ramanujan delta function in weight 12, for example, gives this relation here. So here I have double zetas where the entries are odd, and they are also, again, a multiple of zeta 12. And this is, in weight 12, this is the first time where this somehow happens. So in weight 10, I don't have some interesting relation between zeta odd, except for this one here. Okay, and this can be made explicit. So how can we get these coefficients? And they come from period polynomials. So let me recall what this is. So first, by Vk, I denote homogeneous polynomials in two variables, x and y. So maybe I should have written this. So these are rational polynomials in two variables, x and y, of homogeneous degree k minus 2. And then if I have a cusp form of weight k, then its period polynomial is given by the following integral. So the notation is pfxy. So this is a polynomial with complex coefficients. And this is given by taking this integral here from 0 to I infinity, so on the imaginary axis. And I take this polynomial here times f tau. And this converges here. So if f is a cusp form and I send tau to I infinity, then this goes to 0. And this here will actually give a polynomial of degree k minus 2 with complex coefficients. And now, for this story, I will just be interested in the even part of this polynomial, which I denote by a minus. So meaning I just take the even monomials. And then the space of polynomials where this guy lands in can also be described explicitly like this. So wk minus are now all polynomials of homogeneous degree k minus 2, which satisfy this simple relation here. And then one can show that this integral here is in this space after also extending by scalars. And the proof is just using the modularity properties of this function f. And then the statement is, this is not just in there, but actually this space here gives all period polynomials in weight k. And this is due to work of Eichler, Shimura, and Manin. which states that if I send f to its even period polynomial, then this is actually an isomorphism from the space of cusp forms to this space wk minus, where I need to divide out this part here. And so this can actually be extended to a version where I, so what this here actually is, you should think of being the period polynomial of the Eisenstein series. So actually, there's an extended version due to Zagi, where I start in the, oops, this should be an M, where I start in the space of modular forms, meaning the cusp forms plus Eisenstein series, and then I get an isomorphism to C with this WK minus. Okay, so basically this means all modular, somehow this WK minus can be seen as the modular forms in weight K. And now, if I have a polynomial P.
Just to make it clear, one question, can I?
Yes, please.
By modular forms here, you mean the full modular forms, yeah?
Yes, so this here is always, maybe I should write it that, this is for SO2Z, so for level 1, the full modular group. Thank you. This is also a good question because maybe later something appears in level 2, but this story here is everything in level 1.
Okay, thanks.
And now if I have an arbitrary polynomial, P of, again, in this VK, meaning homogeneous degree K minus 2, then to this I want to assign a collection of rational numbers by making this change of variables here in this polynomial. And this will be, again, a polynomial. And then I will pick these coefficients out of this polynomial here. Yeah, this gives for a polynomial P, this gives me a collection of rational number, which I call beta P RS, where R plus S adds up to the weight K. And then the more precise version of this theorem of Kaneko-Zagier, where I mentioned that modular forms give relations among double zeta values, can now be stated like this. If I take a period polynomial, meaning I take an element of this space WK minus, and I use this to create these rational numbers beta, then this relation here holds for these double zeta values, where these R and S are odd. Yeah, and for example, if you take, if you start with the Ramanujan delta function and then calculate the period polynomial, then and construct these betas, then you will get the relation I mentioned before. And here I say this is 0 modulo some single zeta, but actually you can also work out the explicit coefficient, which you get here as a multiple of zeta k. Okay, so this is now the story for modular forms, and now I want to go to the finite story. But before I give the definition of finite multiple zeta values, I want to give the definition of so-called symmetric multiple zeta values, which are related to these classical multiple zeta values. And for this, I need to mention this regularization, which I mentioned earlier also, that so the statement is as follows. So in the definition of multiple zeta values, the first entry needed to be greater or equal to 2, because otherwise the sum doesn't converge. But you can extend this definition by also allowing that k1 is equal to 1. And then what you can define is a polynomial where the coefficients are multiple zeta values. And this can be done uniquely by saying that somehow the zeta 1 is just the variable t. Then if the first entry is greater or equal to 2, then this polynomial is just the constant, the corresponding zeta value. And then the third condition is that they should satisfy this harmonic product formula. Doing these calculations with the sum we did before, one can do on a purely algebraic level without thinking about convergence. So this here is maybe just a rough statement, but that's why I give an example here. So to find the definition, for example, of this harmonic regularized multiple zeta value zeta 1, 2, t. So the third condition states that this formula here should be satisfied. So this is just zeta 1 times zeta 2 equals zeta 1, 2 plus zeta 2, 1 plus zeta 3. So these here are, by this condition here, should be just zeta 2, 1 and zeta 3. This here just should be just zeta 2, and this here should be t. So we see that zeta 1, 2 t is just this polynomial here in t. And in general, if I have some zeta value which starts with some 1s, then this will be a polynomial in t, where this highest exponent of t is the number of 1s I have here at the beginning. Yeah, and these are the harmonic regularized, or sometimes are also called Staffel regularized multiple zeta value. And they also shuffle regularized multiple zeta values, where you replace the third condition by, instead of taking the harmonic product, you take the shuffle product. Okay. And now with this, we can define the so-called symmetric multiple zeta value. So this is for an arbitrary index. So these k's can be arbitrary. We now define this zeta s for symmetric. And what we do is we take a sum from A to R, where R is the depth. And for each A, we somehow cut this index here. And then we take the beginning and turn it around. So here you see it's K1 up to Ka. And here it's Ka plus 1 up to Kr. And then sum everything up and take a negative sign here. Yeah, and one can show that this definition, I mean, these are now polynomials here in T, because it could be that these Ka and Ka plus 1 are 1. And then I would need to take the regularized multiple zeta value. But one can show that all these non-convergent parts, they cancel out. And this is actually a multiple zeta value.
In the summation, A should start from 1?
No, this is also a good question. So this should start at 0. And what this 0 means, 0 just means that that this part here is not there. And here I take the whole index K1 up to Kr.
And the power?
And this is just 1. And so then this
0.
sum here is 0, and you should interpret this as just 1.
Because K0 does not exist, so.
Yeah, so if A is 0, then this part here is, or this whole part is just 1. And you just get the zeta value of this index. Also, if K is R, then you get here everything, but in the reversed order, and this here should be seen as 1. So somehow maybe I should have defined that I say that some zeta of some empty index is 1. Okay, and then one can check, which is not obvious by this definition, that these objects also satisfy this harmonic product. So it's exactly the same formula, which is maybe not so obvious from this definition, but this is also not so hard to show. So how do these look like? So for example, in depth 1, what is this by definition? Well, I have two summands. I have A equals 0 and A equals 1. And the first part here is just zeta kt, and the second part is -1 to the k zeta kt. Yeah, and clearly if k is even, then this here is just 1. So I have 2 times zeta k. And if k is odd, then this is just 0. Yeah, so somehow in depth 1, the only zeta values which survive are the even zeta values. So you might say, well, then maybe we get less. So maybe the odd zeta values, they vanish. But the answer, or the statement is that this actually gives all multiple zeta values. So this was proven by Yasuda, that the space of all multiple zeta values is actually spanned by these symmetric multiple zeta values. And if you want to get your zeta 3, for example, then you need to consider the symmetric multiple zeta value of higher depth. Then you need to go to depth 2, to get your depth 1 zeta 3. Yeah, and so in particular, if we have relations among multiple zeta values, we can also obtain relations among these symmetric multiple zeta values because they span the same space and they are just linear combinations of each other. So for example, if you use double shuffle relations to prove this relation, you can show that this is, for example, equivalent to this relation here. Yeah, and maybe try to remember this relation here because this will also appear again later in another form. So zeta S41 minus zeta S14 plus zeta S32 equals 0. Okay, and now I want to give the definition of finite multiple zeta values, and then later we will see what they have to do with these symmetric multiple zeta values. So this here is the definition of multiple zeta value, and we want to make this finite. So one thing, so this is an infinite sum. So one way to make this a finite sum is by restricting this summation here, saying that all these m's are smaller than some p. And let's say p is a prime number. Then if all these m's are smaller than p, what I can do is I can consider the sum modulo p, right? Because all of these m's are invertible modulo p. And then which p should I take? Well, we just take all of them. So I take the tuple over all primes. So, and where does this now live in? So this now lives in the infinite product over all primes, where each entry here lives in z modulo pz. But actually what we want to do is we want to divide out the direct sum over all primes, that modulo pz. And what does this mean? Well, this just means that two of these tuples are considered to be the same if they just differ at finitely many places. Yeah, and this will be the definition of zeta A, because this here is usually, this ring here is usually denoted by A. Okay, and this is the definition of finite multiple zeta values. So here again, in clean. So for an arbitrary index set k, so here we don't need to worry about any convergence because all these sums are finite. I take, so define the finite multiple zeta value, I take the tuple over all primes where I restrict the summation, and then I can take this modulo p, and this lives then in this ring A here, where this fp is just z modulo pz. Okay, so so on the first look, this doesn't have to do anything to do. So I mean, this looks similar to the definition of multiple zeta values, but now this lists on a different planet, so it's not obvious why this should still have a relation to these classical multiple zeta values. But the first observation is this ring A here, this is actually a Q algebra, so this is easy to see that we can embed Q into A, and the reason is because we divide out this direct sum here. It's because if I have some rational number A divided by B, then of course I cannot take this modulo P for all P, but so there are just finitely many divisors of this denominator here. But because I consider this object in this quotient here, I don't care about finitely many places. So for example, if I want to consider 3/10 in this ring here, then I will have problems at the primes 2 and at the primes 5. But at this place, I just can take any value because this doesn't matter. But at all other primes, this rational number makes sense, modulo P. And therefore, we can embed Q into A, and we get in a Q algebra. Okay. So therefore, we can consider the Q vector space spanned by all these finite multiple zeta values, which I denote by ZA. And also, it's easy to see that if I take a product of two of these, where the product just means component-wise multiplication in this infinite product, then they also satisfy this harmonic product. Because if I go back here, if I multiply two of these sums component-wise, then I can always do the same combinatorial manipulation by saying, taking this is greater than this, and this is greater than this, and they are the same. Because all of these sums are always smaller than one fixed p. Yeah, so the algebra structure is somehow similar to the classical multiple zeta waves or to these symmetric multiple zeta waves. They all satisfy the same harmonic product formula. And now, how do they look like in devs1? Well, in devs1, one can show that they are all 0. And this is not hard to see. So in devs1, I just take the sum. M goes from 1 to p minus 1, m to the k. And then I can take a primitive root modulo p and write m as sum a to the j, and take a sum j goes from 0 to p minus 2 of this expression here, 1 over a to the k to the j. And then I see this is just 1 minus a to the k to the p minus 1. And then we see modulo p, this here is just 1, and then this is 0 modulo p. So this is really elementary number theory that in devs1 they are just 0. And in devs2, you can show that they look like this. So if in devs2 I take the finite multiple zeta value, zeta a, k1, k2, then here, so this is the Bernoulli number of, so at the prime p, this is b of p minus k1 minus k2. And now you say, wait, what if k1 and k2 are big? Then I have the negative Bernoulli number here. But here again, we can use that we are calculating in this ring A. So we can assume that this p is big enough. So for a given k1 and k2, I can assume that this number here is actually positive, and therefore this Bernoulli number makes sense. And this is also not so hard to show. What you do is you use this sum for this formula by Faulhaber for the sum of powers. The sum of some powers. And there's an explicit formula which involves Bernoulli numbers. And this is how these Bernoulli numbers come into this game here. Okay, so by this formula we see in particular, because all odd Bernoulli numbers are 0, except for the first one, we see that these double zeta values, or these finite double zeta values, are 0 if the weight is even. And if the weight is odd, then we expect that this here is actually not 0. But this we cannot show. And actually the sad part of the story is that we can actually not show for any value that this is not 0. So for example, to show that this here is not 0 in this case, for example, there's this conjecture that there are infinitely many regular primes, and there's this criteria by Kummer which relates regular primes to the divisibility of the numerator of Bernoulli numbers. So for example, if you were able to show that there are infinitely many regular primes, then you could show this here, because then we could show that there are infinitely many primes such that this Bernoulli number here does not vanish. Yeah, but the statement is that this is not an easy question to show that something in this ring is not 0. But of course, we conjecture that that these objects are interesting. So nobody believes that they are all 0.
How about zeta s? I mean, this is expected for zeta a, and zeta s is the same situation.
No, for zeta s, we know that some parts are not 0. For example, here zeta s in devs1 is just 2 times zeta k, and we know that zeta 2 is not 0. So zeta s k is just 2 times zeta 2. Yeah, but thank you very much. So there's a difference here. So in devs1, for example, zeta s k is 2 times zeta k, but here in devs1, zeta ak is 0. And now for these finite multiple zeta values, there's some kind of analog for the doppel-shuffle relations. It's not exactly the same, but there's this harmonic product. But the shuffle product does not hold this, but there's a so-called linear shuffle relation. But there's, again, a family of relations where we expect that they give all relations. And using these, one can show that, for example, this relation holds for finite multiple zeta values. So zeta A41 minus zeta A14 plus zeta A32 equals 0. And now, if you remember the relations I showed you before, then the same relation also holds for the symmetric multiple zeta values. But I will come back to this in a minute. First, also there's some observation which relates these objects to period polynomials. And in this case, so in the classical case, the relationship was between double zeta values where both entries are odd. And here it seems, if I consider finite multiple zeta values of depth 4, where I have even 1, and I try to find relations among these objects, then the first relation I find is in weight 12. And then if you do more calculations, you somehow see, or this was observed by Kaneko and Zagi, you see that the number of relations you obtain coincides with the dimension of cusp forms. So there also seems to be a strange connection of cusp forms and these finite multiple zeta values. But as far as I know, there are actually no results in this direction. But since this seminar is on periods, I wanted to, again, try to fit in these period polynomials, or these periods of modular forms, because one might expect that, or one might hope that maybe there's an analog of this theorem of Kaneko and Zagier by maybe giving explicit formulas for these coefficients coming from maybe period polynomials. But anyway, let's go back to this part here. I said this relation is also satisfied by the symmetric multiple zeta values. And then one might expect maybe they satisfy all the same relations. But this we already saw is not the case, because in depth 1, they differ. In depth 1, the finites are 0, and in the symmetric are, in the even case, they are not 0. But still, there's this conjecture here. This is now the Kaneku-Zagier conjecture, which states that we have an algebra homomorphism from the space of finite multiple zeta values to the space of multiple zeta values. But after dividing out this thing here, this pi squared z, so this, I mean, I can also write this as zeta 2. So this just means that all these even zeta values get sent to 0. And the map is by sending exactly the the finite multiple zeta value to the corresponding to the class of the corresponding symmetric multiple zeta value in this quotient here. Yeah, and this is a really surprising conjecture because it relates these two objects from two different planets. One is these real numbers, and the other is living in this fancy ring. And then this conjecture, together with the dimension conjecture by Zagi, also implies this dimension conjecture for these finite multiple zeta values. And this dividing out this pi squared here, it just gives this additional factor here, a minus x squared. So this here just means, if I would write it as the sum of two things here, I would just subtract the dimension of two weights lower, which comes from multiplying with zeta 2. Yeah, but of course, this conjecture is still a conjecture because we cannot even show that this space here is not trivial. So in particular, we cannot show that this map is actually well-defined. Okay. So therefore...
Excuse me?
Yes, please.
So, is this upper bound, like the classical case?
Oh, this is a good question. This I actually don't know. So you ask if we know if these numbers we obtain here actually give an upper bound for this.
Yeah, because, I mean, the other case, right? The link
Yeah.
control and the Terzoma already show this is upper bound.
Yes. So for this space, we certainly would have this. But for this, I think no. But I'm not sure. This is a really good question. Thank you. Okay, so now we have this conjecture, which somehow is really surprising. This Kaneko-Zagier conjecture between these real numbers and these tuples. So what I want to present now is somehow giving a kind of evidence why this conjecture might be not completely wrong. And the way we want to do this, introducing these objects here, which we denote by Z and K. So they will be defined as some Q series. And then we will consider this Q at the primitive root of unity. And what we will do is we will send, so originally these will be some Q series. And then we will set Q to be some nth root of unity. And what we want to do is we will send here Q to 1 in some analytic way. And what we will do here is we will set Q to 1 in some algebraic way. And somehow show that if we have some relation here, so there are some families we can prove, then taking these two limits here, we will obtain the same relations for these two objects, which somehow supports this conjecture, because this conjecture says that these objects satisfy the same relations. Okay, so let's define these Zns. So as I said, it's a Q series. So again, for some index k, we define this Z and k. So it also depends on a natural number n and some q. And this is this truncated sum here. And then we take this part here. So in the numerators, just these powers of q. And here in the denominator, we have this q bracket here, which is just given by this thing here. So this can be just seen as a q analog of the natural number m. So here, if I would take q goes to 1, then this here is just m. Yeah, so these objects can also be seen as q analogs of multiple zeta values. So what does this mean? This just means if if I take here the n goes to infinity and then q goes to 1, or the other way around, it's easy to see that these objects give back multiple zeta values. Because if q goes to 1, this here goes to m to the k, and here everything goes just to 1. But what we want to do now is to not send q and n independently to something. We want to combine them by saying that q is an nth root of unity, and then they are somehow connected by this n. And then we want to see what happens if we then send n to infinity. And then we will see that we will actually get these symmetric multiple zeta values. So this is the first statement, namely if we take this q series, and for the q, we plug in e to the 2 pi I divided by n, then the limit n goes to infinity exists, and we denote it by this psi. And surprisingly, this psi can be written down like this here. And this should look familiar, because if I replace these two entries here by t, then this was exactly the definition of symmetric. So if I write it like this, then this was the definition of symmetric multiple zeta values. But the difference here is now that in the first t, we have pi I over 2, and in the second t, we have minus pi I over 2. So it's not exactly the symmetric multiple zeta value. But if we look at the real part, what is the real part? Well, I have a pi I here. So these are polynomials in pi I. And the real part is I always need an even power of these. So I will have, because an odd power will always be in the imaginary part. And then even the real part will contain some even powers of pi. So if I divide out even powers of pi and consider the real part of this limit, then they're actually the same as these symmetric multiple zeta values. Yeah, so yeah, and this is really, you should think of sending q goes to 1. I mean, what we do is we send q to 1 here on the unit circle, because Q here is an nth root of unity, and we send n to infinity, and this just means that this here goes to 1. In particular, we can also show there are some relations among these Zn for n large enough. And if we can show this, then in particular, this theorem gives a relation among symmetric multiple zeta values modulo pi squared z. Okay, so this is the symmetric part. And the finite part is as follows. We can show that if we collect all these ZPK, so sorry, here I should have written ZPK at some primitive root of unity. So here we set Q to be some primitive root of unity. It doesn't actually matter which one we choose, but for each P, we just choose one primitive root of unity. And then we show that this element here, if we take modulo this ideal P, which is generated by a 1 minus zeta P, then this equals the finite multiple zeta value. And for this to make sense, we need to show a few things. So first, we need to show that this actually makes sense. So first one can show that these ZPK at the primitive root of unities are cyclotomic units. And then one sees that if we divide out this P out of this ring here, then this is isomorphic to just ZPZ. So this element here we can really view as an element in ZPZ. Otherwise, this statement here doesn't make sense because this here is a tuple of elements in Z modulo PZ. But due to this, this here makes sense. And also this Q bracket evaluated at this primitive root zeta P is just M modulo P. So in the definition, 1 over this Q bracket, this just goes to M. So in particular, again, if we have a relation for the ZP, which are true for all P big enough, this gives a relation among these finite multiple zeta values. Yeah, and this somehow then gives this evidence that these two objects somehow come from the same object here by taking this analytic limit here and this algebraic limit here. And this here, I said it corresponds to setting Q equals 1, because if I divide out this ideal here, I mean, this basically means if this here corresponds to Q and I divide out the 1 minus Q, then what I basically do, I set Q to 1. And here I send Q to 1. So it should give the same object, even though, of course, this is just somehow a fake interpretation of what we are doing here. Okay, so this is this. So at the last part, so this was the main thing I wanted to tell. So introduction to finite multiple zeta values and this surprising conjecture, but also that this nice interpretation here using these multiple harmonic Q series. And the last part, I just want to mention a work in progress. So here I should mention, so this was with Takeyama and Tasaka already 2 years, or no, 3 years ago. And an ongoing work is now together with Anzawa-san in Nagoya. And we consider higher level zeta values. So the story before was somehow level 1. And somehow you can define level n versions by also allowing some nth root of unities in the numerator of the definition of multiple zeta values. And there are several reasons why this should be called level n, because, for example, for n equals 2, there are also some relations to modular forms of level 2 and so on. But here in the finite world, what I want to mention are just these values here. So these you can call alternating finite double zeta values. So without this part here, this is exactly the definition of the finite double zeta value. But now we also take minus 1 to the power m. And this I want to indicate by taking a bar here. So this r corresponds to the first position. So I take minus 1 to the first position. And if I take 2 bars here, then for both positions, I take a -1 here. And if I would just put a bar here, but no bar here, then I would just take -1 to the n, and so on. And also similarly, I can define the single zeta k bar by just taking the this sum here. Okay. So we are studying these objects now, and we are interested in the space fk spanned by these double alternating finite zeta values. And the first, so this is now just I take all of them. So this R and S can now be bar or not bar, and they can be all natural numbers, such that the weight equals k. And the first statement is that for odd weight, these are quite boring. So the finite multiple zeta values, they are also boring in depth 2, because we saw they are all given by these Bernoulli numbers, so they are all the same. And this is also the case here for odd weight. But for even weight, it seems that they are interesting, and they are not all a multiple of some fixed zeta value like here. So for even weight, we can also prove a family of relations, which look quite similar to this period polynomial relation. So recall that for a polynomial p, we defined these coefficients beta. And then in the classical case, if I take p to be a period polynomial, then the statement of Kaneko and Zagier was that a relation among double zeta values is satisfied. And the statement here is now that actually for any even polynomial, we can create these coefficients and then also take some power of 2 here, and we get this relation here. And for example, if we take this simple polynomial here, then we get a sum formula of these alternating finite double zeta values. Okay, but so in this case, somehow every polynomial works and not just period polynomials. But still, I'm hoping that there might be some connection to period polynomials, maybe of higher level. So here the statement is, in contrast to this classical case, we can take any polynomial and not just period polynomials, and we get a lot of relations. But the second statement is that there seems to be more relations, and some relations which we cannot prove in this even weight case for these bar versions. For example, this relation in weight 6, I still cannot prove, and it doesn't follow from the theorem before. And in general, we expect that this space fk is spanned by all these finite alternating double zeta values where both entries are odd. And moreover, we expect that they are linearly independent, and therefore they form a basis of this space. But this is still a work in progress. But yeah, this is actually everything I wanted to tell you today. Thank you very much.
Okay, thank you, Henrik. Any question in the recorded session? Eunice, I think I stop recording and then we go to